Yeah, we're good.
We're good. All
Okay.
right. Some wise words first, or I
No,
can start
the wise words were
already.
outside
Oh,
recording.
okay.
I don't want these on the record.
All right, people. Thank you very much for joining us again today, this afternoon. And I will continue the lecture series in the biological optics with something of more an applied topic, and that is called spectral imaging. First, I will talk to you about spectral imaging, a little bit of the theory. In the coming lecture, Dick Sterenborg will also explain you more about the application of spectral imaging in medical diagnostics. But I will focus, after my introduction, a little bit more on the forensic applications. It's not totally outside of medicine. It is forensic medicine. It's about blood and victims on crime scenes and those kind of things. Well, the second part of this lecture will be about fluorescence diagnostics. So that's more medical. That will be about oncology, finding tumors and imaging tumors. And if there's still time, I will talk to you a little bit about photodynamic therapy, which is based on the same principle of applying a photosensitive dye, which selectively accumulates in the tumor, and that you can use to visualize the tumor, but also to treat. So these fluorescence diagnostics and photodynamic therapy are very much related. I'm Maurice Aalders. I'm working here at the same department as Dirk. My chair is forensic biophysics here at the AMC. And I'm also directing the Covalent Center, which is the Netherlands Center for Forensic Science and Medicine. So in that specific center, we're kind of organizing all research, all academic research that's currently being done in the Netherlands together with the NFI and the National Police. So in that way, we're Sjoerd has doubled, 2 Sjoerds in the image. Welcome, Sjoerd. So I'll just start with the introduction. As you can see here, a couple of images, fluorescence spectroscopy, where we've selectively labeled the tumor. I don't know if you can see my pointer here. Can you see that? I've shared my screen, so it must be okay. So which nicely outlines the tumor after application. So it selectively accumulates in the tumor, and we can nicely visualize it with spectroscopy. And here's brain tissue. And here's some more application about the forensic stuff, which will come later. Well, you've heard about biomedical optics. You've heard a lot about the application of light in medicine. And from all the toolboxes that we have, I will specifically go more into the monitoring spectroscopy, which is a very common technique, of course. It's used a lot in analytical chemistry, but we're also doing that in medicine, which is slightly more complicated. Spectroscopy, just some slides here about the spectroscopy itself. It's kind of separation of your components for analysis, which you can do based on charge and weight. You can do it based on the more electrochemical interactions. You can do it on weight and solubility, but you can also do it on the optical behavior. And this is what we will, of course, in this lecture series go into. So it's spectroscopy, optical spectroscopy. For us, it's a non-contact means of chemical analysis, which is always good if you're talking about pathology. If you're talking about tissue, not touching and knowing what it is good. Also in forensic applications, it is very much preferred, of course, because it's a non-contact, non-destructive way of studying forensic evidence. Can be biological traces, body fluids, but can also be wounds on crime victims. And it's, of course, based on the interaction of light and matter. I will go a little bit more into that, but you will hear a lot more about that also from Dick Sterenborg in the next lecture. And we say that spectral response is material specific. It's depending on the components that you want to measure. Now, spectroscopy can be done in several ways. One way is to do a point measurements, in which you have your light source, your white light source, all the wavelengths in there, or if you want to go to the infrared part, you have your infrared light source, couple it into a glass fiber, which brings the light to the tissue. In the tissue, it's distributed, and when it's remitted from the tissue, it can be captured again with a fiber, and that to bring the light to the spectrograph to split it into its individual wavelengths. But we're talking a lot about hyperspectral imaging here, and that's combining spectroscopy with digital imaging. And in that way, you will not get your chemical information of one side, but you can do chemical mapping of components over a larger surface. So you get spatial and spectral information of the object under investigation. And this is, of course, ideal in a lot of applications. If we're talking about medicine, we can inspect larger organs. It takes you a lot of time to do spectroscopy point by point. For instance, if you have a esophagus, it's like a big surface tissue, so that will take a lot of time. And by looking at it with spectral imaging, you can analyze this whole surface in once. Each pixel will get a spectrum, so you can chemically analyze each pixel. So also for remote sensing, it's very well known for studying agriculture, for forests, for anything from a distance. Food industry, it's used a lot in food. Conveyor belts, scanning of candies, of everything that's made, meat and fish are using it a lot. So food industry, clinical diagnostics, as I just told you, but also in forensics. Because in forensics, if you're going to a crime scene and you want to look for a specific type of tissue, or you want to look for a specific trace, biological trace, you don't want to sample the whole crime scene point by point by point, micron by micron. Just want to make an image and then do an analysis of your spectra, and then that will yield the location of your traces and hopefully also the chemical information. I'll come back to that later. By the way, if you have, I can open up the chat here, I think. Yeah. No. Yeah. If you have questions, just interrupt me because I think it's much more useful if you interrupt me if you don't understand anything. Well, if you don't understand something, because I will rattle on and that will not make sense if you're lost somewhere. Or you can post your question in the chat. And I will also look in the chats if you have questions. Well, our hyperspectral imaging, I will tell you just a little bit about the processing, spectral pre-processing, but Dick Sterenborg will do that much more for the clinical applications. And I will do that a little bit in the medical forensic application. So I will look at the age estimation of blood stains. I will look at the age estimation of bruises, and that's for child abuse. So if you can get an estimate of the age of a bruise, we know when this child was hit. It's very useful in, well, making up the whole story of reconstructing the whole events of how these bruises came on the child. And it's a non-contact analysis of tissue parameters like wounds and forensic traces. With the advantage, it's non-destructive, fast, mobile, and very versatile, as I just showed you. But there's, of course, it's not so easy. It's not like you can use the camera and you have your absorption spectrum. We need to do some spectral processing first. Well, this is what I said. It's a generic technique to get spatially resolved chemical information from objects. You can measure the intrinsic pigments in the skin. For instance, if we're talking about a bruise, the intrinsic pigments are blood, higher levels of blood, or bilirubin, the yellowish, greenish stuff. That's a reaction product of breakdown of blood. Or tumor may have different components in there, and which you can use if they have specific optical properties to get a contrast with. Like in this case, this is a basal cell carcinoma. We can add labels. We can add specific fluorescent or absorbing components. In this case, this is a tumor with nanoparticles. And by specifically looking at that emission peak of these nanoparticles, we can create very nice contrasts to find this tumor. And we can also functionalize these nanoparticles to treat. It's highly multi-scale, so you can go from satellites, which are watching our Earth with hyperspectral cameras and spectral cameras, onto microscopy and anything in between. So it's very multi-scale, and there are many, many applications. So tumors, brain tissue, babies. Sometimes these babies become yellow. That's bilirubin. If they cannot get rid of the bilirubin, which is a breakdown product of blood, quickly enough, there's a condition called jaundice. And this bilirubin will accumulate in the tissues, and if the levels are too high somewhere, you can get brain damage. So this child has to be watched very carefully for bilirubin, and bilirubin, fortunately, has very distinct absorption peaks. So if you do hyperspectral imaging of this little baby, you can measure the absorption, you can find the bilirubin, and then you can, well, do an intervention. So that's basically by putting the baby under the blue lights, because that will break down the bilirubin. Also, oximetry is, of course, a very well-known application of spectroscopy. Oxygen-rich blood has different spectral properties compared to non-oxygenized blood. So that's the deoxygenized hemoglobin. And if you measure spectra, you're looking at the pulsating component. You can measure the oxygenation in the hand, for instance. And you can do that, of course, on the whole body to just get a very quick full body diagnosis, chemical analysis of all the areas on the body. So it's a very useful technique. Sound quality is okay. Okay. And it also becomes available very quickly. So the technical advances, they go so very fast, and I'll show you that later, that some 10, 15 years ago, we were walking around with huge devices to patients to measure on very small tissue types. And now we can work with very small, almost DSLR-like cameras, and we can measure very high quality hyperspectral images. So these are all very fast. And you can see that even on a chip, very normal cameras, very small, to get you that chemical information. This is an example of us doing stuff at crime scenes. So this is a mock crime scene in this case. At the NFI, the Netherlands Forensics Institute, which is a very close partner of our group. Here we developed this hyperspectral imaging to find bloodstains on crime scenes, to find them very quickly, but also to measure the age of deposition. So the great thing about spectral imaging is that you can measure like chemical components in objects. And if these chemical components change over time, you can use that change, of course, to calculate back to the time that a trace, in this case blood, was deposited on the crime scene. And then you have a real time point. You can put things on the timeline. And this is very important. It's almost the holy grail in forensics. And we're working on that for a long time with the police and the NFI. So spectroscopy is very simple. This is light in, light out, Lambert-Beer, Beer's law, Lambert's law, depending on what country you are and who takes the credit for this. But we usually call it Beer-Lambert, which is the light going in, light coming out. There's an exponential decrease in the intensity, which is governed by the absorption coefficient here. And this is the path length. So the path through the tissue or the cuvette or anything times the mu A. That will give you the decrease. That's the power of the decrease of the light. So in practice, very simple. You measure the light in, the light out in these very nice cuvettes. You know the path length, so you can calculate the mu A. If you did it for all the colors, you have the absorption spectrum. So the absorption behavior is a function of wavelength, and that you can compare to reference spectra that you can find in, for instance, literature. Do you know what components are in there? So that's you measure a spectrum, you know the path length, and you have your composition, or you can create your contrasts. So the path length is a bit of a problem if you're moving on to reflectance or remittance spectroscopy. There the light went into a material, it scattered around, and then it escaped. It was remitted. And the scattering behavior, as you have all learned, is not same for all wavelengths. So the path lengths are different for each wavelength. So you have to correct for that in order to determine this mu A as a function of wavelength. But that's, of course, very difficult if you have like a multiple layered system, for instance, blood on the substrate. Light goes in, will scatter around, and it will go into the host substrate. It will scatter around, and then eventually it will escape to the camera. And that all is a path length, and that's all different for different wavelengths. So there's a problem there. And this signal decrease is, of course, also influenced by other things, like the geometry of the source and detector. So if you have a source from one side, I've lost my camera, but probably it's somewhere there. Here I am. If there's a source from one side and a detector on the other side, that will be a different geometry. You will, for instance, have more specular reflection in your camera, on your sensor. If you have it co-aligned, you will pick up another part of the remitted light. So the source detector geometry is very important. Then the absorption scattering. Also the structure, of course, determines the light, but also the amount of specular reflection. Light source spectral properties, light source spatial properties, and the detector properties in terms of efficiency, yield as a function of wavelength. So these components are all in there, and you have to correct for those before you get any decent signal that you can analyze, that you can compare, for instance, with a reference spectrum. So that's the difficulty, and that means we have to do some calibration to correct for the detector efficiency, for the source detector geometries. You have to do some spectral pre-processing to correct for differences in distances to the object. If a camera measures on an angled or curved object, for instance, the distance to the object is different, and also the angle at which the light escapes and it will reach the detector is different. You have to do some spectral analysis, of course, maybe to decompose the spectrum in all its contributing components. And you have to do some image processing to present your end result to the user. And that can be the doctor, it can be the forensic specialist, but someone who uses the technique. And it's also very important how you present that. So these are all involved in spectral imaging, basically, in spectroscopy. And this all requires that extensive, how do you say that, toolbox that you already obtained during the starting lectures in this course. So we'll look at it a bit closer, more in detail, to calibration. You have to do the calibration first. This is the same list as I just showed you. It's required to compensate for source spectrum. A light source doesn't have a flat spectrum, so there's not an equal amount of each color in the light source. So you have to correct for that. It's the sensitivity of the detector. Some detectors are very sensitive for the UV part of the spectrum. Some are very sensitive to the infrared part. And, well, our eye is very sensitive to the green part of the spectrum. So you have to correct for that. And also the optical transmission of the system. If you're using glass fiber, there are some optical transmission effects. If you're using lenses or you're using filters, they all have their own optical transmission. So basically are wavelength dependent, and you have to correct for that in the calibration phase. Then there's spectral pre-processing. There are a lot of algorithms for that too. You can do a smoothing, so you can get rid of the noise by smoothing. You can do an offset correction. The offsets are basically probably due to the distance to the object. You can do standard normal variate correction. And with that correction, you're basically correcting for the intensities of the spectrum. So if you have a spectrum which is twice as high as another spectrum of that same spectral image, because the distance is further away or closer by, then you correct for these distance variations. And there are all kinds of multiplicative scatter corrections. That's the difference in scattering. So there's a lot of pre-processing algorithms. And very important for these pre-processing algorithms is that you're not throwing away your information. So as I just told you, you're correcting for the amplitude of your spectrum by using, for instance, an SNV. But that if you want to measure the concentrations of a certain component, you're basically throwing that information away by correcting for these amplitude differences. So you have to be very carefully by adjusting your spectrum using the spectral pre-processing. You have to be very aware of what information basically you're throwing away, because that's what you do when you're applying these. And I'll come back to the spectral analysis, and then we have to do some image processing, and I'll show you that later. The data analysis, say we have a very nice calibration, we did a very good pre-processing, and then you will end up with something that consists of your absorption properties and your scattering properties. Now, say you want to unmix your spectrum. You want to get all the contributing components and how much these components, blood, fat, water, melanin, for instance, in the skin, how much these components contribute to the total spectrum. Then you have to do a spectral decomposition. So you have to get all the elements out of this, out of your spectrum. Well, you can do spectral unmixing. That's the main thing. There are several ways to do that. You can, of course, do principal component analysis. And I think you all know what that is. You're looking at the elements in the spectrum which creates the largest variance. That will be the first principal component. Then second principal component that has less influence on the differences between the spectra. And in this way, with principal component analysis, you can get a very good separation of the different components in a spectrum. There's spectral angle mapping. These are all statistical methods. They do not require any reference spectra, but these are just there to get maximum separation of your components in the spectrum. So it basically decomposes the spectrum in various components that contribute differently to the total spectrum. You can also simulate the light through tissue using an inverse Monte Carlo. I think you all are aware of what the Monte Carlos are. So that's basically simulating light transport through tissue. And in that way, you can get, for instance, the path length. So you can get that path length effect out of your spectra in order to get pure absorption spectra. And or you can do a more analytical light transport model, such as the diffusion approximation of the light transport equation. And this diffusion equation is used a lot in our field. And that depends on the application, which algorithms you use. So a little bit more on the different steps. So if you want to find targets, you want to find pixels corresponding to a particular material. So say you have the reference spectrum of blood, and you can then analyze all the pixel in your spectral cube to see if there are spectra that resemble the spectrum of blood, for instance. And then you can give that a false color, as I've done here. This is blood in some scene, some forensic scene. And here you can nicely see that by comparing the spectra of all the pixels in the spectral cube, we can see that we that it nicely comes up with the blood. Oh, I'll just. So that's target detection. If you're looking at anomaly detection, that's basically if you have a large scene, you can find pixels within the scene that are anomalous to the general background content of the scene. So that's basically generating the normal, which is your reference spectrum, and then you can detect all the pixels that have a kind of separation from that are different from that. And you can, for instance, do that by spectral angle mapping. There, every point in the spectrum is part of a vector, and you just look at the difference in angles between the two vectors of the normal and each pixel. And if these are within this normal vector, it's background. If these are largely different, it is something that you're looking for. That's anomaly detection. In this case, the tumor in the skin. So you're measuring the whole back of a person. You just say, this is normal skin. Use that as a reference factor, and you start to look for anomalies in that field. Same thing is with crops. Police is flying over cornfields, for instance, and looking for marijuana plants. So they're looking for anomalies in that field. And you can detect that because the pigments in these plants are different from the pigments in other plants. And that's done in anomaly detection. Or you can do a classification that's segregating the scene into a variety of unique classes, done by clustering. And so you can create different clusters. So what pixels are a cluster? They resemble each other very highly. So for instance, for the small intestines, peritoneum, spleen, colon, bladder, they have distinct reflection spectra. So you can use principal component analysis and k-means clustering to create these different clusters. And then by selecting a cluster, it will give you images like this. So that way, you're not doing anomalous detection, but you're just creating differences. And then the knowledge that you have to put in there yourself is, of course, the anatomical knowledge. So this is, during the processing, there's no knowledge necessary, but for the interpretation of these images, there's always knowledge necessary because it just gives different colors. These are just separated. And this is also a very nice application of spectral imaging. And unmixing, of course, if we're looking at the, each pixel is composed of a mixture of many materials usually. You're not measuring only blood, but also the host tissue, or not only this tumor tissue, but also the host surrounding it. And then you have to do some unmixing. You can like subtract, for instance, the spectrum of your host material, and then you end up with the spectrum of your pure components, which you can further analyze. And if you can do a time series, you can determine changes in scene composition. And that's done, of course, a lot in the tumor progression. And you can create different photos at different times, and it will add the element of time in there. You can see if a tumor grows, if the composition changes, and in that way get a much better view of the progression and if there's an intervention necessary. So these are the different algorithms, or the different classes of algorithms that you can apply. Now we'll go a little bit more into the spectral unmixing, if there's no questions on this first part. There's a kind of different regimes that we're working in. If there is a very shallow surface, and for instance, very low order scattering is assumed, so the light just penetrates very shallow in a tissue, there's very low order scattering, and if we can estimate the path length, we can do, of course, this Lambert-Beer law. We can estimate the path length. If the light goes deeper and there are many scattering events, then the field will get diffuse, and then we can use the diffusion approximation. And the difficulty is the part between that. There's this low order scattering regime that's very difficult. But we're looking now to diffusion approximation, since that's the most common one used in spectral imaging. And say that it is basically a matter of bookkeeping. It's very simple. You can construct your light transport model by looking at all the separate components. So you can describe your source. In diffusion theory, it's usually a diffuse source, or a source that diffusely emits light, infinitely white, but that's something that you can describe. So there's a source term, your incident radiation, or your radiation being created inside the material. There's, of course, the radiation absorbed by blood. There's a loss term. There's stuff going in the substrate. There's another loss term, and you can describe that using the optical properties of these different layers. And there's radiation scattered and remitted by the blood, and there's a radiation scattered by the substrate. And by carefully describing this, say, energy balance, you can set up like a transport model like this. And this is an example. It is a kind of one-dimensional model with infinitely wide layers, infinitely wide light source. This is a kind of one of the approximation solutions of the radiative transport equation. And it was used a lot in the early days, still used a lot in the paint industry, and we also use it, and it's called the Kubelka-Munk approximation. And there's some approximations to use these kind of models. Scattering dominates the absorption. That's, of course, necessary, as you already had, because we need a diffuse field. If there's too much absorption, your field will never progress enough to get diffused, to lose the sense of direction. As I said, it's infinitely wide, the whole thing, so it's one-dimensional photon flux going that way or that way. There's diffuse illumination, no polarization effects, an isotropic homogeneous medium of finite thickness and infinite width. So it's a very thin layer, and then we can describe the transport through that single layer, the flux going up and going down. And this ratio is determined by the optical properties of that thin layer. That's what behind this whole theory. And there's a lot of things that can be said that is, of course, not true in reality, but it's more accurate than you may think. So that's the good thing for us. And for us, it's a two-layer medium, so we have a two-layered Kubelka-Munk model. And it looks a bit like this. Doesn't matter so much. This is the like the end result of this derivation, where the RS in this case is measurements on the substrates, in this case filter paper. versus a white reference. So then we have a corrected spectrum coming off the substrate, as I showed you in the energy balance scheme. And this A and B, they are corresponding to the optical properties. So the absorption coefficients, the scattering coefficients. And they're not straightforward, absorption coefficients and scattering coefficients, but there's some relation here. So this is how we do it. We measure on the bloodstain versus the white reference on the substrate. Can be a wall, can be carpets, can be skin, versus the white reference. And then we have this one, and we fit these parameters to it, the Kubelka-Munk parameters. And then we can calculate these two, which are more the common absorption and scattering coefficients that you already have heard about in this lecture series. Well, this is something that further assumed if we're now selecting one particular application, namely blood. It is medical forensics, so that's blood. We have to deal with a lot of blood. We assume that there are only a limited amount of components in there. Same holds when you're looking at a tumor. Same holds when you're looking at specific types of tissue. But there's a limited amount of components. In this case, there's oxyhemoglobin. That's the red pigment in the blood. There's methemoglobin. So if the blood is exposed to air, it will oxidize, and then it will turn into methemoglobin. The iron will go from 2+ to 3+. And then there's a denaturation process, because it's a protein, the hemoglobin, that will fall apart, and it will turn into hemichrome. So we assume these three elements are in that material. So then we can further define that it's a linear combination, the absorption of oxyhemoglobin with a certain concentration, methemoglobin and hemichrome. So we can further decompose the absorption, and then we have derived the MUA and the MUS, and then we can further decompose the absorption into these three components by doing a fit to it. And for scattering, we assume a Lorentz mean scattering. So that has to do, as you already probably have in your toolbox, the different scattering regimes. There's Rayleigh scattering, there's Lorentz mean scattering. That has to do with the wavelengths and the size of the particles and the indices of refraction of the particle and well, the fluid around it. So these are the light model as we can set it up then. So this is the total equation here. With these are the different optical property containing parameters leading to the absorption and scattering coefficients. Two assumptions. There is a kind of behavior, scattering behavior, wavelength depending scattering behavior like this, and it's kind of linear combination, the mu absorption of these three components. Not the intensity decrease. It's not a linear combination because there's, of course, they're contained in here. So but the absorption can be decomposed into these three components. To make the whole story a bit complete, for one example application here, measurement on the white, measurement on the bloodstain, on the substrate, and on the white, selecting a certain wavelength, which is very specific for our components. If these components were proteins or if these components were water, you would go more to the near-infrared region. But since this is the example for blood, we can use the visible part. You do a least squares fit of the one-dimensional transport equation. Wow, this is we just put this in between. We just do a correction for differences in distance, standard normal variate correction, and then we get an output. That's the concentrations of the three, and then we get some sort of total hemoglobin component, but that's not necessary. So this is the thing that we do. That's all on paper. That's all theory. But how do we do it in practice? We can measure spectra just with a normal camera. We have a normal camera in our telephone. It's a color camera, like in a DSLR, and each color pixel is basically 4 separate pixels. So there are 2 green pixels, 1 blue pixel, 1 red pixel, and that these 4 pixels make 1 color pixel. So the resolution is basically a quarter of what you may think, because 4 pixels are used to make 1 color pixel. And the 2 greens are there because our eye is much more sensitive for green light than for blue or for red. So that's a little bit of the balancing of the image. But these 3 large wavelength bands are not enough to resolve an absorption spectrum of, for instance, blood or bilirubin or hemoglobin or those kind of things. So we need more wavelength. We need a higher resolution in the spectrum to resolve these absorption spectra. And this is what we do with spectral imaging. We're not acquiring 3 wavelength ranges, but we are acquiring this spectral cube. So we illuminate the object with white light. All the colors are in there, and we calibrate that. And then we just use a monochrome camera, a non-filtered camera, because every color camera has this Bayer filter, these 3 color filter in front of it. So we just use, in normal worlds, a black and white camera, no color filtering there. And then we put a filter in front of it, which just emits the blue light, and then less blue, and then orange, and then red. 200 of these filters in front of the camera. And then we obtain something like this, which is a spectral cube with 2 spatial axes here and 1 wavelength axis in the other direction. And this means with a spectral cube, you can either look at an image of 1 specific wavelength to look at contrast, for instance, or you can select a pixel and obtain a full spectrum at that specific position. That means you can analyze each position on in that image. You can do a chemical analysis of all the positions of your field of view. And this is again a crime scene-like. So you can now analyze and looking at these components. Is it blood or is it something else, or where are the traces? By just looking at each pixel, compare it to a reference library, do a decomposition, and then indicating it to the crime scene expert. So we selected here 1 pixel and we get something. This is reflectance, mind you, not absorption. So wavelength here, this is like green to near infrared. This is reflectance, so a low reflectance is a high absorption. And this is kind of the reversed spectrum of blood. High absorption here in the green, low absorption here. And there's an extra peak here, which is methemoglobin. So there are like 2 peaks almost disappeared. And here's an extra peak, which is methemoglobin at 630 nanometers. So I know it is blood and it is of a certain age. So that's the extra information. Before I come to the applications further, there's some hardware developments lately. We used to do real filters in front of a camera. So that means that was like big cameras, cooled cameras, big filter wheels that would just put a filter sequentially in front of the camera each time. So it was a huge machine, a lot of noise. The patients were more likely to die because they're scared from the camera than from their pathology. It was kind of intimidating, and it was very limited in terms that it was very multispectral. So there were like 8 or 9 filters in there, so you could grab 8 or 9 areas in the spectrum. Not so much if you want to resolve chemical components. Well, this is it's based on another principle. This is there are a lot of cameras, but this is one it's the latest, and this only acquires 1 line of light of the scene. This line of light is going through a dispersive element like a grating or a prism, those kind of things, that will split all the pixels in that line in their separate wavelengths, and then the image is recorded. So each image contains the spectral information of 1 line in an image. And then the entrance slit or the spectrograph is slightly moved to obtain the next line, next line, next line, next line. So you get spatial scanning of a scene. The same geometry is used in remote sensing. These cameras are used a lot under airplanes. And then you're flying over I don't know, a forest or something, and you obtain each image line as you fly along. So that's the scanning. You will get this image line in your camera. It's split by dispersive elements and imaged on the sensor. So you can get a full spectral analysis of the scene that you're flying over, like a super panorama hyperspectral cube thing. So it will that's very easy. It's a very small camera. It's very small, like a DSLR, and it's very simple to use. So also for practitioners, which was not the case before. I showed you the image where we were working on a crime scene kind of scene, and that required the 2 physicists, a laptop, all the cables and extra, and that's not very practical. If you're going to, for instance, the OR, where there are a lot of personnel walking around. The doctors want to do their operation, and there are a lot of machines now. Not practical in crime scenes when there's a lot of blood and you can contaminate the whole thing with all the wires and the physicists walking around. So that's, if things become more practical now and will be applied a lot more in the near future. So that's it's a very good time for spectral imaging. And this is what I just told you. Or this is what I just explained was push broom scanning. So you get your spectrum as a line. You can also have a spectral snapshot imaging. And that's not using 4 filters in front of the pixels, but like 16 or 17. They will give you separate wavelength band, and they will give you a snapshot, but a very low spatial resolution, of course, because you're sacrificing spatial resolution in order to get more wavelength bands. Or you can, of course, scan the camera wavelength and then looking at it with the camera to a certain scene. You can also obtain the reflection, but then the whole ambient lighting has to be dimmed, which is not practical usually. It is practical in a surgery situation where you want to go in with an endoscope where things are dark anyway, and then you can scan the light source and obtain the spectral information. So that's the tunable light source. So there are some considerations depending again on the application. Stare down is, this is slow, this is faster. Snapshot imaging, limited but fast. There's a trade-off, that's it. And then you obtain the spectral cube. It has many applications, a lot of things in oncology. Dick Sterenborg will show you more applications in oncology to find a tumor. And he will also, by the way, tell you more about some spectral analysis methods in neural networks. So you can also, of course, feed a neural network with a lot of spectra, train it, and then use that to analyze your spectrum, if things are a tumor or not, more binary decision. But that will come next time. Well, this is an example that we used on burn wounds. Here you can see a real clinical example. Noisy because of very low intensity at the short wavelength. Here you have going more into the blue, into the green. And now you're slowly moving into the red. And you can see all the different aspects. You can see the change. I don't know how well this movie runs on your computer. But if it's like 10 frames at a time, it will not be so nice. But I can stop it at some point. There's a taskbar in the way, but okay, here it is. So here, when you go to shorter wavelength, like 480, 496, you can see these areas turn dark. We're still at a high absorption peak of blood, but also on a waste product of blood, like bilirubin. And then if we continue more, we go between 500 and 600 nanometers. These are the distinct absorption peaks of blood. Oh, shit. Oh, sorry. We go here. Then you can see more contrast, so you can determine the perfusion, basically, look at more specifically at the blood. And after 600, so these are the absorption peaks of blood here. And if you can see, if you still remember the absorption profile of blood, that will decrease after 600 nanometers, then the scattering becomes dominant, and later on the water in tissue becomes dominant. So here the blood is not so much visible, but it's more like the blood and the scattering of the tissue. You can see it nicely. Well, you see it has information depending on the wavelengths that you're looking at. You're selecting different components. You're creating different contrasts for different components by selecting the wavelength. So that's all very nice for clinical diagnostics. And this way, at some wavelengths, you can find tumors easier. We can find blood stains easier. We can find other body fluids easier in the crime scene. And this is what we did on the burn wounds to see if we could predict if a burn wound would heal by itself, or if a scar would come up, or if a surgery was necessary. That was a decision that we were trying to find here. Now this is the visible part of the spectrum. We can also go beyond visible. So the visible is RGB photography. We can go to the infrared. Specifically important if you're more looking at water absorption peaks. In forensics, we can easily detect body fluids like this, because in the near infrared, our clothes don't have any color anymore, because the colorants that are used in the dyes that are used in clothes, they do not absorb if you go beyond like 800 nanometer. So then the traces become visible. So it would be very hard to do an inspection for traces on this black t-shirt without any chemical tests. But if you then move with your camera to a longer wavelength, then the color disappears. You're basically all dressed in white, and then the dirty stuff becomes visible. It's a good thing our eye is not sensitive to that, because that would be not so nice. We can also shift further, which is also spectral imaging, go more to the further infrared. So that's thermal imaging, but it is basically taking part of the spectrum to create a thermal image. So we know there's radiation from a warm object, and we can calculate it back to the original temperature if we know the emissivity of the object, and if we know the distance or the water in the air between the camera and the object, because that will also, of course, influence the amount of radiation coming from an object with a certain temperature. So there's some conversion steps to create like a picture like this. And this is useful, again, for all kinds of medical applications. For instance, for diseases, pathology, which have inflammations, like rheumatic joints, for instance, or if there's a tumor, there's more blood. So these areas are hotter compared to the areas surrounding it. So we can use thermal cameras for diagnosis. Forensics, we are having a project where we're looking at the time of death, because the bodies cool down after death, and we can nicely record it with these cameras and then calculate the temperature loss after death and calculate that back to the time of death for forensic applications. So that's also spectral imaging, selecting a part of the spectrum which gives us heat information, which is super. And this, of course, also is good for water, for plastics, those kind of things. So also for surveillance applications. But you are here for biomedical optics, so I'll not go into that part. If you're really interested in all the forensic surveillance, policing, then you can come to me. Oh yeah, some images here of a body cooling down after death in the morgue. This body was brought in there. We have a body donation program where we can study bodies that are decomposing, so to speak. So we can look at the temperature change over time, and we can see if that matches the model, our predictions. We also have a grave field here. We can bury people and look at the decomposition, measure all kinds of things, also with spectral and thermal imaging. But this is a body in the morgue. Put it on the chat, but does anybody know why it's so modulated, the signal? Is it still breathing? Are we too early with putting this person in the fridge or not? That would be a sad conclusion of the whole story. But you can put your suggestions in the chat that I'll discuss. And these long wavelengths are sensitive to water, of course. There's a huge water absorption. So if you want traces, you can find them here. Not visible in the white light, but in the infrared, you can nicely see these traces. And again, heat for inflammation changes. So this is it. It's a kind of pulsating, which is not good, but I will get it off the screen now. And so this is the RGB imaging that you can do, but you can also do spectral imaging beyond the visible to create, for instance, on this t-shirt, sorry, this is in Dutch, but it's a quick lecture, Dutch 101, blood fleck, blood stain of a couple of days old. Analyzing a single pixel, we can nicely create a spectrum here of all the wavelengths, and we can see here the nice absorption peaks of oxygenated hemoglobin, and we can nicely see the absorption peak of methemoglobin. So there's some conversion already of oxyhemoglobin into methemoglobin, and if we know these kinetics, we can calculate the time of deposition of these blood stains on the shirt. So that's all very nice if we look at the chemical analysis. Bruises, also imaging of bruises, back to the medical forensics. If we look at the reflection spectrum, here a spectral cube scanned from 400 to 1000 nanometers, comparable to the thing that you just saw in the burn wounds, we can see a maximum contrast around 480 nanometers compared to the normal skin, and that is bilirubin. So that is the greenish, yellowish stuff that you often see around the red part in a bruise. You can see a ring usually because it's a small molecule, so it diffuses faster through the skin. So if you have a bruise, you very often see this yellowish, greenish part around it, and that's the bilirubin. And this will create a certain contrast with the skin surrounding it. So you can select, there's another toolbox, you can select the wavelength with which you can image these bruises. And this is very important because often if there are bruises because of child abuse, because of domestic violence, because people were hurt during robberies or those kind of things, they will go to the police. The police will send them to the community health service, where they will be judged by a forensic physician, and then everything has to be documented. Now, this particular bruise was not very well visible with the white light, so it's very hard to make pictures to put in a file of this crime. But if you just image it with like 480 nanometers, you would get a very nice contrast of the bruise to put in a file. Like here you have the maximum contrast, and here it's already disappears. And if you would expect this is white light, it's just one white, very white skin. So this is also used to create contrast in these pathologies, these bruises, which are not so interesting medically, but forensically they are very important. And so creating contrast, this is a blood fingerprint set in blood on a red table, very hard to visualize for the experts. But if we go to 550 absorption maximum of blood, we can nicely see a contrast. And as a bonus, we can analyze again a pixel and then get the spectrum back. So here, this is what we started with. This was the intimidating device, which was brought to the patients with a mercury lamp with water cooling, and a filter wheel here, and a huge camera and a filter wheel here to create 8 wavelength or 9 wavelength images. And this is scaled about, so this is very small, easily handheld, progressing. Finally, we have this small camera. So the medical application, I will just go before we take a small break. Sorry for me rattling on. The gases developing and escaping. That's an interesting question. Can you give me more of a context? Sorry that I ran over this.
Oh, it was a reply to your question about why the thermal image of the body was kind of moving.
Yeah.
So I think it would be like the gases which develop after dying in your body.
There is a very good. There is indeed the gases are escaping. Body starts to decompose. There are gases coming up from the microorganisms, eating you away basically. Then you start to bloat, but it's a very slow process. It is well after this first cooling process. So in the long-term decomposition, there is something in there. That you're right. In the short-term stuff, it's not like this. So it is, and it's much more complex than it really is. I'm a bit ashamed now to say what it is, but you can guess further, just to think on. Just some forensic application. Forensic medicine may not be so very well known to you, except from these doctors walking around on the crime scene in full makeup and high heels and very well dressed. The forensic doctors, physicians in real crime scenes, they're dressed in these white suits, which are terrible because they're not breathing. They're like garbage bags. Everything is covered, and they just do a first examination. Also, the physicians that are working at the community health service that go very often to crime scenes, also for suicides, to see if there's a crime involved. They are dressed in this whole thing, and they basically do a first examination to look at the wounds and to sample the body. So to sample, for instance, traces of gunshot residue or any other fibers and stuff on the body. Then the body is put in a body bag and brought to the forensic lab, basically. Can be the NFI. They have their own medical department where the forensic physicians do an autopsy, looking at everything in and outside of the body. And that's all in our clothes, of course, because you cannot contaminate the body. Or it's brought to Alkmaar that receives body from the police for scanning, for CT scanning, MRI scanning, to see if there are like internal bleedings that may be the cause of death, and not so much the violence. So looking to see if it was really the violence that was the cause of death, or if there was some underlying medical problem. That's what the forensic physicians do. It's very early done. Also in the 16th century it was started, but then routinely used from 19th century on. And you can look at gunshot wounds, weapon wounds, everything. There's a lot of books got its own specialism, and usually based on human interpretations. So we need something like a medical diagnostic techniques, which is not like depending on the human interpretation, but it's much more objective. So the objectivation of your measurements, of your diagnosis, that's what we want to get with these devices. So here's an example of wounds. The wound imaging, this is another like bruise. There's something that you can see. I don't know if it's very visible on the transmitted image, but there's a wound here. But if you're using blue light, which has a very high absorption, you can see a nice contrast here. And even in darker skins, where the melanin is contained in a very small superficial layer, and it's not so much absorbing in the longer wavelength, you can see this nice contrast appear, which is super important for the police, in the community health service, for instance, to get the bruise documented in the file of this victim. Also here, what we can do with the light sources, with spectroscopy, basically, this was something that had to be inspected, and when these forensic light sources were used, but now at 450 nanometer, you could really see the nice contrasts of light reflecting, but also darker areas here, where there was some remains of a wound that, well, looking at the pattern, is more like a bite wound, and it's very well visualized in this way. And you can also use multiple wavelengths in order to get a contrast like this. So with the normal techniques, you cannot do it. By diagnosing with spectral imaging, spectroscopy, forensic light sources, you can get this very nice image, which can be used in the file of this victim to, well, confirm a story, for instance. So this is used a lot. Also here, very short wavelength imaging. This, of course, has always the disadvantage that you cannot go very deep in the tissue. So if there's a hemorrhage, bleeding much deeper, is a bruise, you will not see it. But what we do here is we induce fluorescence, and because the fluorescence components in the skin change when there is a traumatic injury happening, like bite wounds again here, collagen changes, it creates cross links, so the fluorescence change. You can see this nice bite wound here, which cannot be visualized in any other way. So now we're not looking at the absorption properties of this tissue, but now we're looking at the fluorescence properties, which is a very nice thing to use to get this contrast. So all spectral imaging, but we can of course do more, and that's what I already was telling you, more about time resolved stuff. I will go quite quickly over this to give you a break. I already told you that, but now I'll just cover this and make you think a little bit more about this. So we're talking about bruises, the development of bruises. It is important to determine when a bruise was caused. When the child is presented to the pediatric doctor or to the family care person, and it has multiple bruises on the body, there can be a story like, oh he or she fell off the stairs, and it's got all these bruises. Now, people used to look at the different colors of the bruise, but that's not really saying something. You probably have heard about the blue veins here and the green veins, or why the sky is blue. You must have heard something about that. That's your scattering behavior. And the same scattering is also very tricky and fools you when you're looking at wounds. Because when a bruise is deeper, it will turn blue, because the green and the red light will see the bruise, will reach the bruise to go down deep to that depth and will be absorbed more compared to the blue light. So the blue light will scatter around and will come out of the tissue. If you're looking at these vessels here, they will look green, some people blue, depending on the thickness of your skin. If they are a little bit deeper, also the green light will not penetrate the tissue enough to see the vessel, and it will scatter around and come out of the tissue to your eyes, and your eyes are more sensitive to the green. So then your vessels will look more greenish. If they are very superficial, like these spider veins you can have in the nose, well, some people have that, or on the skin, or port wine stains, very superficial, large stains, large vessels, then it will turn red again, because then all the wavelengths go deep enough to see that vessel, and then it's just the absorption properties of blood, which is much less in the red compared to the green. So the depth totally gives you a different, or determines what color you see. And that's of course very tricky, because a bruise can be a different depth, also depending on a different location. So it may look like the bruise has different colors, which may be caused by different times. So maybe a long-standing child abuse, but it can also be that it was just caused at one time and just at different thicknesses of layers above it. So looking at the bruises, well, say something about the time that is not done anymore. That was done a long time with these reference cards with colors. But we as physicists know that this is not the way to go. Visual inspection, visual determination of that age is just not possible with the naked eye. So we need to do something smarter than that. We know this. This is the bruise. Blood escapes from the vessels, diffuses into the skin. At some point you will see it, because then it's close enough to the surface. Depending on that depth, of course, it will be blue or it will be red. That's the blauwe plek, as we call it in Dutch. Black stain is called in other cultures, but it has different names in other cultures. We call it the blauwe plek, a blue stain. Then the hemoglobin, which does not belong there, is converted to bilirubin, and that will give you this greenish color around it. The molecule is 4 times smaller, so it will diffuse faster through the skin. So it usually creates a ring around the area of hemoglobin until it disappears. So what we want to do with hyperspectral imaging is hemoglobin derivatives, the blood and the bilirubin, and we want to measure the fat. And how we use these examples to come to the age, I will tell you later, because we're already an hour on our way and it's too long for online teaching. I know, I'm guilty, but I have so much more to say. So let's take a 10-minute break. Just relax and look in the distance. That's a free advice. Not go to another screen now, because then you will stay as focused on screens as you are now. So look far in the distance and walk around, and see you in 10 minutes, right?